Okay, pause and copy, pause and copy, pause and copy, pause and copy. Now, let's see. What do we have here? Well, I think more typically, when talking about a convergence sequence, I will say something like, as n goes to infinity, comma, an goes to L. It's maybe the simplest way to think about it. So if my sequence ends up giving me a number, a real number L, so I'm working on the limit, I'm working away, and I get a real number. If I get a real number, that means the sequence is convergent. So if I get a real number, the sequence is convergent. Any other situation, that is divergent. Okay, let's do an example to illuminate as we do. So we'll take an to be this basic alternating sequence, -1 to the power of n. So what does this look like? If I write out a few terms. So I start with n equals 1, that gives me -1, and then I get +1, then I get -1, then I get +1, then I get -1, and so on and so forth. So having a gander at this thing, is an approaching anything? Okay, when n gets larger, if I choose larger and larger n's, is an kind of getting closer to any single real number L? No, it is not. This is oscillating forever. So we say oscillating or alternating. So this is divergent. And sometimes we'll say are there two L's in oscillating? Sure. Okay, so again, looking at my little rectangle here, as n goes to infinity, this sequence here is just going back and forth, -1, +1, -1, +1, -1, +1. It is not approaching any single real number L. Okay, another example. Erase. Example 2. An is equal to, we'll start with the alternating bit, then divide by n. This one's a little bit different and a much different conclusion. So writing out the terms, I'm going to get -1, and then I'm going to get 1 over 2. Then I'm going to get -1 over 3. Then I'm going to get +1 over 4. -1 over 5. So this one we can see is oscillating, but we have this division by increasingly large integers. So I will spoil the surprise. This is going to converge to 0. Because sure, it's going back and forth, negative, positive, but in both cases, it's getting closer to 0. Okay, that is my intuition. But to demonstrate that, I'm going to use something called the squeeze theorem. Squeeze theorem. So I indicate that I'm going to use this approach. And what this approach requires is that I stick my an into an inequality. Well, I'm going to start by noticing that this alternating factor is at most 1, and it's at least -1. Okay, so look at that inequality. Hopefully you agree. Now the idea is I want to take this basic inequality and I would like my sequence to appear in the middle here. So what do? I take this inequality and I divide all three pieces, 1, 2, 3. I divide them all by n. And something good will happen, I promise. So I get -1 over n. Then I get my alternating bit over n in the middle. And finally 1 over n at the end. Okay, what's the point of this? Well, the point is that I have stuck my sequence, an, between two very simple sequences. Okay, so I've taken my relatively complicated sequence, stuck it between two very simple sequences, and I know that the limit here is 0, and the limit here is also 0. Okay, that's clear as day. Okay, if I look at this fraction here, and I let n go to infinity, I of course get 0. So my conclusion, and I'm using the squeeze, what's called the squeeze theorem here, is that because this side goes to 0, and this side also goes to 0, my middle part goes to 0 by squeeze theorem. Okay, so I took my sequence, I worked on it, and I found a limit to be a real number. So I don't need to say this, but I'll say it anyways. This, maybe I'll say it more clearly. Say an is convergent. Boom.